Welcome to a lesson with Dr. Powell. Let's take a look at power set posets and the sum to summand problem on such a poset. This is done with a Mobius matrix or Mobius solving map. But we're going to be interested in top summands and seeing kind of how those work. So first, let's look at a very simple one. Maybe a power set where arrows represent inclusion with just one thing. Now, its two standard basis elements are 1, 0, and 0, 1. What are the solutions of this? Well, this is solved simply by 1 minus 1, and you can check. Because 1 plus -1 is 0, and just 1 is 1. So this is a nice solution. This one has a very simple solution, simply 1, 0. Notice that as we move up this poset from here to here, what's the contribution to the top? This guy contributes a -1. This one contributes a 1. As I move upward, contributing a -1 from here, and then a +1 from here. This pattern of 1 and -1 is visible as I go to other types of power sets. Let's do 2 elements. Okay. Now, let's look from the bottom and consider standard basis element that looks like this. Now, the solution to this, you can check, is 1, -1, -1, 1. Think 1 plus -1 is 0, 1 plus -1 is 0, and all of these added together is 0, and a 1 on the bottom. So this is a nice solution. Notice that at the bottom, the contribution is a 1. On this level, the contribution to the top is a -1. And here, the contribution is just 1. Okay, from each of the standard basis vectors. Similarly, if we did a power set on 3 things, 1, 2, 3, and then we have 1, 2, 2, 3, 1, 3, then we have 1, 2, 3, and let's see, so 1 is included in there and in there, 2 is in here and here, and 3 is in here and here. Okay, and the empty set is included in each of those. Okay, now looking at this, from here, from this guy, if I had a standard basis element with a 1 there and zeros up above, the contribution to the top would be, well, let's think. At this level, in the solution, I would have -1s. At this level, we would have +1s. And at this level, a -1. So this would contribute a -1 to the top. At this level, you'd contribute, so yeah, let's see, yes. So this one would contribute a -1 to the top. At this level, we would contribute, let's think, well, just pick something right here. 1, notice that a diamond shape is created from here, here, here. So it's really like a poset on 2 things in structure. And so it's going to contribute, well, from 1 to -1 to 1, it's going to contribute a +1. So a -1 from this level, a +1 from this level, remembering that these are the contributions to the top. From this level, a -1 contributes to the top, and from this level, a +1 contributes to the top. Now, how can we use this to solve summand type solutions? Well, let's start with the idea of a derangement. A derangement is a permutation on say three things, if we're talking about three different things. So it's going to live in S3 such that there's no fixed points. No fixed points, that means nothing's going to map to itself in the permutation. So for instance, the permutation 1, 2 actually fixes 3. It's like a 1 cycle. It'll send 3 to itself. Hence, this is not a derangement. We don't want to use 1, 2. But 1, 2, 3 is a derangement. It doesn't fix anything on the 3 elements. Okay, now actually by inspection, you'll notice there's only 2 possible derangements. Anything else is either equivalent to one of these or has fixed points in S3. So these are the only 2 derangements on S3. How could we count that though from a power set type of diagram? Well, what we could have done is we think about the tops. We think about what derangements are as a summand. It's a summand solution at the top of the following diagram. If we think about the power set poset and think about arrows as being inclusion, and we think about the vertices being labeled with how many permutations there are in each one of those subsets. Things with 2 things have 2 factorial permutations on them. At the top with 3 things, 1, 2, 3, this is like 1, 2, 3, there's 3 different permutations. So then down below, you have 1 permutation on each one of those singleton sets. And then you have 0 factorial permutations, which is 1. There's one way to do nothing on nothing, it's to do nothing. So therefore, there's 1 permutation down here. You have the same arrows going upward. And if you look at this right here, this represents how many permutations in all, but we want to figure out how many permutations are not simply just permutations here on maybe 1, 2, or just permutations on 1, 3, because these would have fixed points, or just permutations on 2, 3, or just permutations on 3, or 2, or 1, because those would have fixed points as well. And this, the identity would be represented down here, a permutation on this as well, to do nothing. And so you notice that what we get is we don't want any of these counted. So what's left over to count would be a summand, meaning derangements, the summand solution at the top. So what we're looking at is we're thinking about contributions. So in our top solution, we would have 0 factorial, but its contribution to the top would be a so negative, positive, negative, positive. So it'd be a negative. So negative down there. The 1 factorial would be a contribution of a positive 1. The 2 factorial, but how many of those do we have? We actually have 3 of those. 2 factorial, we'd have 3 of those. So minus 2 factorial, minus 2 factorial. All those have a contribution of -1. And the 3 factorial itself has a contribution of +1. If you were to add all these up, you end up getting 2 as desired. Now, we could have done this simply in the following way. For this case, we could have done 3 choose 3 times 3 factorial with a plus minus 3 choose 2. So how many sets have 2 things in it, and how many sets with 3 things? 2 factorial plus 3 choose 1, 1 factorial, minus 3 choose 0, 0 factorial. And thinking about the definition of this as 3 factorial, 3 factorial, 0 factorial, notice the 3 factorials would cancel, and we'd be left with 3 factorial over 0 factorial. Similarly, we would get something like this. 3 factorial over 1 factorial plus 3 factorial over 2 factorial minus 3 factorial over 3 factorial in the following way. If we factor out 3 factorial, we're left with 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial, which looks suspiciously like the first part of a power series or Taylor series, e to the negative 1. So this looks like 3 factorial times, or approximately, because it's truncated, we haven't added everything, approximately 3 factorial times e to the negative 1. And in general, actually, if you just use the Taylor series idea, it actually takes care of all the summing for you. N factorial over e, and you round that, should give you the number of derangements on n things. Thanks for watching.